Alright, welcome back to Chapter 14 of Price Analysis, a fundamental approach to the study of commodity prices. In this part of the video, we're going to talk about how an ethanol producer could actually hedge this ethanol crush spread. And this is going to be similar in feel to how the soybean crusher hedged their crush spread, but with a little bit more, with one little thing that's going to kind of complicate the issue for us. So let's try to figure out how to line up our quantities here. So just for reference, it turns out that ethanol futures contract specifications are for 29,000 gallons of ethanol in one futures contract, and that I happen to know is about approximately the amount of ethanol that will fit in a typical train car. So it kind of makes sense as a quantity for your ethanol contract. And here, let's note some how the proportions work out. Suppose you were going to take 10,000 bushels of corn and turn it into ethanol. How much ethanol would you have? Well, we noted above that we get about 2.8 gallons of ethanol for every bushel of corn. So if we grind 10,000 bushels of corn and turn it into ethanol, we're going to get about 28,000 gallons of ethanol. That's pretty close to one contract's worth of ethanol in terms of a futures contract. And so it turns out that a 2-to-1 ratio for corn contracts to ethanol contracts is pretty good because, of course, you remember that corn contracts are 5,000 bushels apiece, so 10,000 bushels of corn would be 2 futures contracts worth of corn. And for 2 futures contracts worth of corn, we produce about 1 futures contract worth of ethanol. So that's pretty simple, except remember that would leave the sale of our DDGs completely unhedged. And we know that a bushel of corn weighs about 56 pounds, and when we take that bushel of corn and turn it into ethanol, we're going to get back about 17 pounds of distiller's grains by weight. And that means we get nearly a third of what we purchased for corn back, and we get to sell it for something whose price closely follows the price of corn. So really, if you're an ethanol producer and you do this 2-to-1 ratio of corn to ethanol contracts to hedge, you're going to be pretty overhedged in corn because you hedged all of your purchases, but you're going to get some of that corn back to sell as essentially as DDGs. And there's really no straightforward way to hedge the sale of DDGs because there's no viable futures contract for DDGs. But you can do something else. There's this concept called cross-hedging, which is when you use a futures contract or some other financial instrument that's not exactly related to what you want to hedge. So in this case, we can't hedge with DDG futures because there is no such thing, but we can hedge with something that is closely related, in this case corn. So we already observed that the price of DDGs and the price of corn is highly correlated. Maybe we can just use corn contracts to hedge DDG prices. And that's exactly what the concept of cross-hedging is. Except usually if the prices of the thing you want to hedge and the actual financial instrument are not perfectly correlated, you shouldn't necessarily hedge it 1-for-1 on a quantity basis. What you're really trying to do when you're hedging with futures contracts is you're trying to minimize the variance of your cash flow. And if you think about that, let's think about the simple case of a farmer's hedge. This equation you should recognize as just the way you would normally calculate the farmer's net price received back from Chapter 4. That's the spot price minus their gain or loss in the futures market, except ignore that B. If the B was 1, meaning the quantity we buy in the spot market is exactly the quantity that we hedge in the futures market, the B is 1, and that's essentially the equation for net price received we did in Chapter 4. Now, what this concept of minimum variance of cash flow does is it says, let's not just assume that we're going to do 1-for-1 on a quantity basis in the spot and the futures market. let's actually solve for the b that gives us the minimum variance in our cash flow. So in preparation for that, these three equations just kind of do some algebraic manipulation and get this cash flow into a different form. And then the next equations compute what the actual variance looked like. So this is going to be from the first to the second to the third. This is going to be just expanding out a variance of a linear combination of random variables. So you would find this in an introductory stat class kind of scenario. And then the variance of the cash flow can be expressed as this thing. And when we want to do an optimal cross hedge, we're basically going to solve for the b that minimizes this variance. And if you think about, like, what do you use to minimize something? You use calculus, right? So if you took the derivative of this expression with respect to b, it looks a little bit ugly, but it's not too hard because the only terms where b's are in it, there's this b squared term, and then there's this b with nothing in it but these constants. So the derivative of this first part would be just 2 times b times the variance expression, and then minus, this is linear in b, so the b is just gone when we take the derivative right here. So if you solve for b, the minimum variance hedge ratio is the covariance of the spot price changes and the futures price changes divided by the variance of the futures price changes. And if you've ever had a basic econometrics class, that should look very familiar. That is essentially the regression coefficient if you were to regress spot price changes on futures price changes. Alright, so sometimes at this point students are a little freaked out because that's maybe the most math we've seen in one equation, in one lecture in the whole class. But I promise you that it will not seem as difficult when we work through the exercises for the lab for this week. So that's going to do it for the chapter lecture videos, and I will see you guys later.